Okay, today I would like to talk to you about X-ray survey follow-up as a driver for extragalactic spectroscopic surveys. We have been blessed in X-ray astronomy over the past 2 decades to have a number of very powerful X-ray surveys missions, ranging from the Chandra X-ray Observatory to XMM Newton to NuSTAR, and then most recently to eROSITA and ARDEX-C. And then also, of course, I want to mention the Swift-BAT survey as well as Integral. These facilities have conducted a number of wonderful X-ray surveys. Just a few examples of them are shown here. And these have detected thousands or tens of thousands or even hundreds of thousands and soon to be millions of X-ray sources, most of which are accreting supermassive black holes out in the distant universe. And we have done a good job utilizing these missions in X-ray astronomy to fill the discovery space of flux limit versus solid angle coverage. As you can see here in the 1/2 to 2 keV band, and here in the 8 to 24 keV band. And the science that comes from all of the wonderful surveys shown in this diagram is fundamentally dependent upon the spectroscopic follow-up that is the subject of this conference, and that's what I'm going to talk about today. So the overall outline for today is I'm going to start with just a few words on the value of X-ray surveys. I'll then talk about the need for X-ray survey spectroscopic follow-up. I'll talk about some successes of that follow-up, and then I'll talk about some remaining challenges. That's the overall game plan for this talk. So let's start on the value of X-ray surveys. So X-ray surveys are truly wonderful at selecting active galactic nuclei, or AGNs. This is because of the penetrating nature of X-rays, as well as the fact that X-rays have little dilution from host galaxy starlight, and thus they have been very effective at finding AGNs throughout the universe and thereby probing cosmic supermassive black hole growth, which is a key part of the galaxy evolution. That's the focus of this conference. In fact, in the deepest X-ray surveys, for example, here in the center of the Chandra Deep Field South, we actually are detecting up to about 24,000 AGNs per square degree at the very faintest of fluxes that we reach. And if you compare that to surveys at other wavelengths, as you can see from this panel over on the right, X-ray surveys find by far the highest sky density of active galactic nuclei compared to any other wavelength. They have a very large advantage in this particular regime. Now, X-ray surveys don't only find active galactic nuclei, they also find lots of other exciting sources. The deepest X-ray surveys are also detecting, particularly at the very faint fluxes, are detecting large numbers of starbursts and normal galaxies. And these are also very exciting. They allow evolutionary studies of another aspect of galaxies, specifically their X-ray binary populations, which evolved in exciting ways over the history of the universe. So this is also important science. And then, of course, these X-ray surveys also provide unique insights into clusters and groups of galaxies, where you're studying their intergalactic media. They provide new insights into transient sources, and they also detect significant numbers of galactic stars. And all of these are also exciting targets for investigation. Now, I want to focus for a while on the need for X-ray survey spectroscopic follow-up. We have a number of aims when conducting the spectroscopic follow-up of the X-ray sources from these surveys, ranging from basic redshift determination through to characterizing the physical properties of the sources, and then more and more ranging toward time domain studies. We know active galaxies are highly variable sources over time, and to fully characterize them, you have to characterize their changes over time. And this can be done with many techniques, including reverberation mapping, for example. And then also, as I've mentioned, we also detect transients in many of these X-ray surveys, and you want to be able to follow those up spectroscopically as well. So these are the broad needs for follow-up of the X-ray sources. And with some notable exceptions. Unfortunately, the X-ray surveys data so far that themselves do not yet provide reliable redshifts. Of course, you do have X-ray spectral information being gathered in the X-ray surveys. That's one of the aspects of X-ray detection. But so far, again, with a few exceptions where you can detect, for example, iron K lines in a few cases, as you can see in this panel over here on the left, the X-ray data themselves don't give you redshifts, but there is promise in the future as better facilities are developed for actually doing that more and more. Furthermore, you can try to derive photometric redshifts for the active galaxies in X-ray surveys, for example, and these are extremely valuable. But unfortunately, they are not as reliable or as precise for the non-active galaxies because AGN just have often fundamentally more complex spectral energy distributions than normal galaxies and are harder to model in photo-Z fitting. Nevertheless, we have had some significant success, as you can see from this panel on the bottom, is just one example of photometric redshifts for active galaxies. You typically can get accuracies of I don't know, a couple percent up to maybe 10%, depending on the quality of your photometric data. And you typically have catastrophic outliers ranging from kind of 4% up to 10% or 15% of the sources. Now, the type 1 AGNs I'll mention in passing are even tougher. Nevertheless, despite the fact that these photometric redshifts are extremely valuable, the photometric redshifts are insufficient, of course, for physical characterization of the sources, which again is one of our important goals via, for example, studies of line emission. And moreover, the photometric redshifts are insufficient for placing the active galaxies in the three-dimensional cosmic structures. You typically have 100 megaparsec or more radial uncertainty. And so that is, another challenge that we're facing in these surveys. And so we have nevertheless had many successes with the spectroscopic follow-up, and I want to talk about that now. So the optical, near-infrared, and mid-infrared fluxes for the X-ray sources coming from surveys can span a very wide range, can span a factor of 100,000 or more. And you can see that here with this diagram. This is just for a single survey in the sky region around the Chandra Deep Field South, surveying about 4.5 square degrees. And you can see the X-ray sources we're detecting there span, well, at least 10 magnitudes, or more than 10 magnitudes in optical flux, from brighter than 15th magnitude down to 26th to 28th magnitude. And thus, many telescopes can and have been used productively for spectroscopy of the X-ray sources from these surveys over the years. And these have ranged from 2-meter telescopes up to 8 to 10-meter telescopes, which are needed, of course, for the faintest X-ray sources. They've all made valuable contributions. And of course, multi-object spectroscopy has been critical here in following up large numbers of X-ray sources economically. Now, thus far, we have generated samples with thousands of spectroscopically identified X-ray active galactic nuclei and X-ray detected galaxies and so on. And these are now being used for powerful studies of, for example, supermassive black hole demographics, physics, and ecology. I don't have time to talk about all of those exciting studies today, but I'll point you to this review paper that I wrote with Dave Alexander. And I also have a number of YouTube videos that give details on such things. But one issue that we persistently faced, and this has been the case since the early 2000s, is that the spectroscopic completeness for the X-ray sources typically drops sharply beyond about 24th magnitude. And you can see, as you can see in these two diagrams here. And so you typically use the photometric redshifts to fill in the fainter magnitudes. And of course, that's extremely helpful, but one would like to have spectroscopic redshifts in that regime. So now I want to finish up by talking about the remaining challenges that we're facing. First of all, there is this faint sources challenge that I've just been telling you about. The 24th to 28th magnitude sources have been a fundamental bottleneck for about 2 decades, and they ultimately limit the science from these billion-dollar class X-ray observatories. And this challenge is only going to get harder in the future with the massive AGN samples from Athena, StarX, Lynx, and so on. And of course, we're greatly looking forward to advances from the ELTs and from JWST. And you can see these are going to be critically important in filling in the kind of redshift 2 and beyond moderate luminosity AGN population is one key place where we expect to find we expect to have a big advance from the improved spectroscopic characterization enabled by these facilities. That's going to be one place we're going to have a big advances. Furthermore, pushing to the very highest redshifts is going to be critically important. Another challenge, of course, is just the large numbers of X-ray sources we find in these surveys. When you generate tens of thousands or hundreds of thousands or even soon millions of X-ray sources, it's just a big job to get spectra of all these things. That's often the rate limiting step toward extracting science, the exciting science. One example I just want to mention is the 5 megasecond XMM survey, XMM SERV survey, which we've just recently completed. This is a very powerful survey. We found about 11,000 AGNs in the LSST deep drilling fields. And fortunately, there are these powerful facilities. Devils is already getting spectra of these fields. Moons, PFS, and foremost waves will soon be getting spectra in these fields. And I very much encourage people, if you're doing spectroscopic surveys in the LSST deep drilling fields, to include the X-ray sources. We'll be happy to work with you to make sure that these can get followed up. Of course, this is going to be even larger with facilities like eRosita. This is this eFEDS survey from the eRosita folks. It's just covering one thousandth of the sky. Here they have 5,000 X-ray sources. They expect to have about 3 million X-ray AGNs over the entire sky, and facilities like Sloan 5 and foremost surveys 5, 6, and 7 will be critical in extracting the science from all of these X-ray sources as well. And then finally, I just want to mention the challenge of time domain. As I said, this is an increasingly important aspect of follow-up studies. And in the deep drilling fields, the LSST deep drilling fields, we are already starting to do reverberation mapping of X-ray AGNs with Sloan 5, and this will soon be being done with the foremost survey. And the idea here is we'll be able to obtain direct supermassive black hole masses for hundreds of X-ray AGNs in these fields. And we also will be able to study BAL variability and reddening variability and changing look quasars and so on. And of course, the Rubin Observatory will provide outstanding supporting photometric data for these reverberation studies as well. So this is another critical challenge for the future. And since I'm tight on time, I will finish up there. And thank you very much for your attention.